Okay, awesome.
Okay. I think I'm audible on Zoom as well, which is, yeah, okay.
Yes.
Um, this is more of an impromptu presentation, but I wanted to go through how to use PyMol to make some good figures. I think it will be helpful for everyone in the group as well. Um, there's a lot of things to know about PyMol. It's very detailed program, but for today, I just want to go through one example of how to set up a scene and how to um, set up PyMol to get a good figure of a ligand attached to a protein. Um,
And which version of PyMol is
this
this?
is PyMol 3. It's the
Yeah,
latest version
yeah.
of PyMol, which
So it might
which I've
look
got. Yeah.
different for people.
Yeah, I think most people started using PyMol 2, but PyMol 3 just came out recently last month, and I think it's much more intuitive now. The GUI is updated very well. Um, when you load up PyMol and you run as a program, you will see this screen at the start. I think the most important drop-down menu, there's two ways to use PyMol. One is the command line prompt at the bottom, and other is the GUI itself. I think knowing how to use both is very important because both are useful in their own way. It's not that the GUI is you can only use the GUI or only use the command prompt. I think you should know how to use both. Um, to open a file, you would go to open and click your PDB file or any other kind of file you have. Another way to get a PDB directly is you say fetch and then PDB code, and it will get the PDB file directly from the RCSB database. This is one of the proteins I'm going to show today, or an enzyme I'm going to show today, and hopefully we can look at how to visualize the ligand more properly. Oh, I think it's um, maybe the wrong. Oops. We oh, there you go. And look and see if we can visualize the ligand much better. When you load the protein, it's going to be on a black background with all the rendering options set to default, which is the worst way to look at it. What I like to do immediately, the first thing I like to do is click the sequence button. It shows the sequence of residues or amino acids at the top, and you can scroll through this entire bar. I think it's really helpful to have the sequence at the top. What I also like to do is go to display. So display and settings are the two drop-down menus which will help um, make the figure look pretty. I go to display, I change the background to white. I think it gives a much better contrast. I also change it to opaque because once you write out a image file, if it's not opaque, it will just show you the transparent protein. I also like to keep, so for publications, CMYK is the recommended color code. If you want your ligands to pop out more, you can use the PyMol one. I think this has much more contrast. So it really depends on what kind of application you have. Um, I like to, I prefer to use PyMol for at the start, and eventually, if I feel like the contrast is too high, I switch to CMYK. Um, Quality, I generally set it to maximum quality. It's going to rebuild the entire structure with maximum quality for every surface. It just takes a while. Okay. As you can see on the command prompt at the bottom, it's set everything to the max quality possible. Another thing in display is orthoscopic view. So right now you see a perspective view of the protein where things which are further behind may appear smaller than things which are closer. I like to work with an orthoscopic view so that I can see more of the more of the secondary structures behind the protein. There's use cases for both. Um, I'll go through an example later where setting it to perspective and setting a specific field of view actually helps see more of the protein. But for now, set it to orthoscopic. Everything else here should be set to default. There's one function called depth Q fogging, where if you see the structures behind seem faded, if you turn this off, the structures which are further behind don't have any fade to them. There's again use cases to have that on or off. I'll set it to off for now. Um, when you fetch a PDB file from RCSB, it will also have waters. So the way to interact with and change anything here is you see this 8DQ8. This is your PDB file. The green dot is showing that it's loaded. If you click on it, it will not load the PDB. You go to hide. So there's 5 buttons here. This is action, show, hide, label, and color. you will go to hide. You can hide a lot of things here. If you don't want to show the water molecules, the small specks around the protein, you say hide waters, and it will hide all the water molecules around. I think this makes it looks much cleaner. Another way to look at this, I would look at coloring it first. Something which is not a uniform color to show some contrast. Depending on what kind of image you're trying to go for, you can color it differently. One of the ways I like to color is color by secondary structure. However, the default options I don't really like, the defaults they have set. So in this case, we can color using the command prompt instead. The command is color, then the color of your choice. I like forest is like a shade of green. Comma, space, you would say SS, which is saying secondary structure. And H is for helix. So it changed the color to a nice shade of green for the helix. You can do the same for, if you're in the screen and you press the up arrow, it will show you all the commands you put in before. So it's a good way to scroll through all the commands you've put in.
Why do you need SS and H?
SS signifies that it's secondary structures coloring, and H signifies the helix. So it will only color the helix in this shade of green. So it's like color, whatever color you want, you can just, it can just be like green, just like for us, but it can just be green. And then SS says, hey, color this green just by secondary structures, and H will be helix. So it will change it. Other ones are S is, I think, for beta sheets. So we can maybe have the beta sheets blue for now. And the loops are L plus double apostrophe. I like to generally keep them either cyan or pink. I think pink should be fine for now. So it just changes the loop. Changes to a red. Okay, so this is for coloring via secondary structure. I think this is a good way if you want to just show the entire protein or entire enzyme, to color them. As you can see, but because we changed the color of the entire protein, the ligand inside is also colored now. This is where our sequence up top will help us. If you scroll all the way to the right, you can see you see the ligands over here. If I select the ligands here, it will make a additional selection. And we can, whenever you make a selection, by default, it will be renamed to SELE or select, I guess. You want to rename this to something, I'll just rename this as ligand.
And were you clicking with like right-hand click or just
the left
left
mouse button.
Okay.
Just scroll it with the left mouse button and then clicked it here. I want to color them differently, so they should pop up more. If you go to color by element, there's a lot of options. I usually pick either the cyan option. I think this looks good. You can kind of see the ligands now compared to before. But I would say this should be the default just to show the protein well, not just to highlight the ligands. Once this color is set up, I would go to settings. There's two things to make sure. One, when you go to rendering and anti-aliasing, this is the option which makes all the jagged edges go away. So if you turn this to off, you can see the edges become very sharp. So setting this to SMAA is a good way to make sure the image looks sharp. This option likes to turn itself off once in a few minutes. I don't know why. So whenever before rendering an image, just make sure this anti-aliasing is turned to SMAA. I think this is good enough for now. When you're ready, when you think, okay, this looks good, I want to render an image. There's multiple ways to go about it. What I like to do is use the command line here. The option to render using a ray trace rendering method is to just say ray, and it will give a ray trace image. If you click anywhere once you use the ray command, it will go back to the original screen. You can also just use ray to ray trace a part of the image. I use a ray 2400, 2400. That is just a ratio. You can have any number there. It's just telling it, hey, pick a box in the center of the screen. with the ratio 1:1 and ray trace just that part. If you see the ends are cut off a little bit, so you can say, hey, the ends are cut off. Maybe I need slightly bigger length than width. And I changed 2400 to 2800 at the start, and the second one is still 2400. I can get a good ray trace image of my protein of interest. If you want to save this image, since it's not saved right now, the option is to say PNG, and then save it. You specify the directory where you want to save it. I know where I'm going to save it, and this is the directory, and then you give it a name. This is the entire directory and location of where you want to save the image. You say comma, DPI equals any number above 300 is good. This will give you how many dots per square inch you want your image to be. I think 1000 is a good value to set it at, so that when you zoom, the image doesn't break. And once this is written, we can go to save the image, and yeah, so this is our test image that we rendered. If you zoom in, it's not breaking the image because we set it at a high DPI, so we can zoom all the way in and see the ligand as well if we wanted to. This is a very baseline way to use PyMol. Okay. But we don't want just a photo of or a picture of just the protein, right? We generally want to look at ligands. We want to look at interactions. There's a few ways to look at these. What I want to show. If you want to look at interactions between chains, sometimes you want to look at interface interactions. This is another PyMol session I had. This is, it doesn't matter what it is, but this is the COVID receptor binding domain of the spike protein. And this is an antibody, which is trying to interface with the receptor binding domain. Here you can see I've highlighted the interface residues, which interact between both of these. The way to do this, and I think what is really important to learn in PyMol is selection algebra. PyMol has a really good wiki. What this means is it's a way to select specific parts of your protein without having to go and manually click every time. I would recommend going through this. I have not fully grasped this either, but you can be very, very specific with what you want to select. For this example, so many sessions open. I want to highlight this particular command. Yeah, this is the PyMol wiki. And
is it from Schrödinger or?
It is from Schrödinger, yeah. The PyMol wiki is, I don't think it's maintained entirely by Schrödinger, but if you go to PyMol wiki, I'll send this link in the lab group chat on Slack. But I have a way to gather all this data. I'll share later how I'm doing that. For this selection, like how I got an interface residue, basically,
Is the structure from Anu?
no, this is actually part of my protein engineering course. We had to design an antibody.
Oh, I see. It's because Anu is working on like the SARS-CoV-2 within.
Oh, I see.
So
I see.
maybe.
I see. So this is from my protein engineering class. So the way I've set this up is I've said, hey, select enter. Enter is just a selection name, where it equals, now BR means by residue. So this is where the selection algebra is useful. I think BR should be somewhere. It's somewhere on this page. BR means select by residue. C dot means chain. So select by residue chain J and N, J comma N. Select the residues which are within 3 angstroms of chain C. So I think chain C is red, chain J and N are blue and green. What it's telling PyMol to do is, hey, select any residue for chain J and N, which is within 3 angstroms of chain C. So when you enter this, it says, hey, selection made with 68 atoms. And if we go to set selection enter, it selected these atoms, which it's saying is within 3 angstroms of chain C. We can do the same thing the other way around and say, hey, select 3 atoms from chain C, which are within 3 angstroms of chain J and N, and it's going to make another selection, which is first atoms in chain C, if you can see right here. So it's a really good, once you learn the selection algebra, it's a really good way to be very precise with the selections without having to go and manually and select everything. Another reason I'm showing this is to highlight one tool, which I think is really interesting, called the mutagenesis tool. I'm not sure if anyone else would need to use this at some point, but what this tool does is you can select any residue you are looking at, and you go to Wizard, Mutagenesis, click on Protein, since we're mostly looking at proteins. It says at the top left, pick a residue. Say I pick this arginine. It's going to let us mutate it to any residue we want, and it will show us the contacts that will be made when we change it to the residue. It will also let us change to any rotamer of that residue we are looking at. I'm not sure if anyone needs to use this right now in our group, but I think this is a very interesting tool just in case you want to look at something, want to look at mutations. Maybe we don't have a structure for the mutation you're looking at. You just want to quickly see if that would be possible. These red boxes are showing steric hindrance. So if we select this rotamer, mutate this arginine to a histidine and select this rotamer, it's showing, hey, there's going to be a lot of steric hindrance. So this is probably not the way to go with our mutation. You can also make these not dependent on the backbone, but I think that's a bad idea because backbone dependent rotamers are probably better in this situation since it's a loop. This is a very, very specific example, but I think it's just a very interesting way to show, hey, PyMol can be used for a lot more than just you making figures. I'll make sure to not change this since it's part of my project, but okay. So once we have our image, we want to say, look at this ligand and be like, hey, how do I make sure I can just see the ligand and nothing around it, right? What I would do is zoom in to the part you're looking at, try to find an angle just to see the entire ligand. Using the scroll wheel, you can, if you scroll down, you can hide parts of the protein to a point where you can only see parts of the ligand. In this situation, using depth Q fogging is useful because it automatically hides stuff which is behind you. It makes it more pale. So I think using depth Q fogging in this situation would be useful. Another setting which is useful is if you go to settings and transparency and cartoon, you can set the cartoons to be 60% transparent. This already makes the visual much more cleaner. You can play around with what you want the transparency to be at. I think 50 or 60% is good enough. But even then, there is a lot of clutter, right? So once you get to a point with your scroll, we will, okay, this is how much I can scroll right now. You just pick parts which you think are cluttered. When you select them with your left mouse button, they'll make a selection. You can go and say hide. You can go and say hide cartoon, and it'll just hide that part of the protein. I think at that point, once you have your angle set properly, you want to go in and hide parts either in front or behind, which you don't want. In the interest of time, I don't want to go through and do this right now. So I have another session where I've this.
Yeah, take your time, no worries.
No, I already have a session where I did that, which is right here. Okay. It's the same ligand and same protein, but I've gone through and changed all the residues, all the cartoon representations, which I thought were getting in the way. I'll show you how it looks fully scrolled up. I scrolled down, got a place where I think most of the cartoon representations are not there, and hid parts which are overlapping with my ligand. In this representation, I want to show how close this oxygen molecule is to a particular part of my ligand. To get this distance modifier, I just use the command distance. I think this is something we might use a lot. Distance, name the distance parameter, which is this, or distance selection, which is just distance 1. I'll say, hey, I want a distance between, I name this oxygen oxy 916, since it's the 916th residue. Give me the distance between oxy 916 and I specifically selected the C4X carbon. If you want to select by default, any selection will select the entire residue. To change this, at the top left, instead of residues, you can go to atom and then select just the atom you're looking at. So I've selected just the C4X atom. And I want to see the distance between the C4X and the oxygen. And delete distance once I can show this. So this is without the command, and once I get the command, it shows the distance and the values for the distance here. But I also want to look at, hey, is this oxygen in contact with something else around it? It's highly possible, right? Because for me, this will depend case by case. But for me, I saw that this oxygen was here for a long time in my simulation. If you want to look at contacts between any ligand and the surrounding residues, there's a few ways to go about it. If I just select this oxy 916 residue and go to A, which is action, find and polar contacts, there's a bunch of options here which tell me where I want to see polar contacts. Hey, do you want to see it within the selection you've made, any side chains in any solvent, just to any other atom? If I select this, I can see, hey, there's 2 polar contacts somewhere close by. But it does not make the selection for me. I might have to go and manually check, hey, where is this contact being made? So instead of doing that, what you can do is use the selection algebra. We said, hey, select contacts around 4 angstroms from oxy 916. If you do this, it made a selection called contacts, which is everything around 4 angstroms from oxy 916. We can increase this to 4.5 if you want. We can mess around with this to see how far we can get. But now that we have the contacts around, we can just be like, hey, show me the contacts as licorice, and it'll show us the contacts with licorice representation. It didn't select the entire residue, so you can go and make a manual selection there. And okay, show me this as licorice. Okay, now it shows the entire residue here. So we can see which residues made polar contact with this oxygen. Since we want to see what they are, we can go to contacts, go to L, which is label, and say residues. It will give the names of the residues which are in this selection. So we can see that the contact is between this, it's between this threonine and between this, I think it's a tryptophan over there. So instead of trying to click randomly within, we can use the selection algebra to get what the contacts are. And this, along with our previous selection, which was this, which was a distance selection, we can show, hey, this is how this oxygen is coordinating with this ligand and the residues around it. If you want to show the difference, hey, this is a polar contact versus this is just a distance, we can go to color and change the color for the distance measurement to something like orange and specify like, hey, orange is just a distance, whereas yellow is a polar contact. So there's a lot of customization you can do. Once you're happy with a particular orientation, a particular depth, you can go ahead and say ray and trace this entire image. This is where some of the more subjective qualities come in. For showing proteins, I think the default colors and default values are good enough. But if we do a ray trace image here, you see a lot of ray trace shadows. The ligand itself is not popping out visually compared to the background. For this, you can do very simple changes, or you can be like me and try and understand color theory to see which colors are good. But what I want to show is different ways already pre-published images show this representation. So this is a reference paper, and look at the way they have shown these ligands, right? They have, for the image C here, there is a big contrast between the background proteins. They've used a very similar scroll-based selection to remove a lot of the cartoon representation. They're using that same depth Q fogging that we are. The ligand itself is very dark blue, and the background is orange. So it shows the ligand in very high contrast to the background, so we can see very clearly where the bonds are and which ligand is placed where. For the image D, what they have done is, because it's comparing two different protein structures, they've made the ligands the same color as the structure that they are part of. So we can quickly see like, hey, this light yellow is the same as this orange over here, and this white is from the same representation as the white representation here. So there's different ways to go about it. I think color is one very underrated way of looking at or when you're selecting or making your images. I have made a very similar, so this is what I ended up with after like doing a lot of going back and forth with different colors and different representations. Once we make this image, this is with the fog. So I went through a lot of iterations. This is with the fog. This is without the fog. There's a this is the different angle, which may not show as much contrast, but very clearly shows the oxygen's much better than this. But this shows the residues much better and shows the coordination of the ligands with the oxygen. So I think going through a few iterations is good, because if you want to have this as a published image, I think putting in some time is good, because that's going to be around forever. Now, I know this was a lot of information. There's a lot more you can do. I was going to show a perspective. Oh, I think it's here. So all of this information, I'm making a GitHub repository for this, so that it's easier for anyone who is coming in as well, or anyone who wants to have access to this information. I'll link this. I guess I'll share this with Shirley as well. This is not a complete guide yet. I'm still adding a lot of things to it, but it's a good place to start off if after today's presentation you want to go and make some images. There's one comparison I wanted to show. So this is a different protein, but this is at the start of PyMol, right? Just without any anti-aliasing, without anything. From this image, we can see, we can't really clearly see what's behind the alpha helix. We cannot see the beta sheets well as well. This is where the perspective view comes in. If this is a perspective set at, I'll show this better here. This is a perspective view set at 70 field of vision. This is clearly showing where all the alpha helices are with respect to each other, how the beta sheets align. And this is where I said, hey, sometimes you need to change the view to be perspective instead of orthoscopic, because you can get these more stylized, cool images to show the difference or show the structure much better. But at this, I'll share this report with Shirley as well, and I'll keep adding more stuff. There's some examples as well on if you want to make a stylized ligand, how do you go about, and set of command line inputs to go with it. Something, hey, I want my FAD molecule to be really pretty compared to the rest of the background. So I'll keep adding examples to this. I think I'm going to add the example I showed earlier to this as well. This is, I think, more pastel colors, more akin to what you would find in a publication. But I'll keep adding examples to the GitHub and keep adding to the guide as well. What I would recommend is to definitely go through the PyMol wiki for if you have doubts, especially the selection algebra. There's a very good color wiki page as well on how to color different parts. You can color the residues with the B factors as well if B factors are present. There's a very in-depth way on coloring. There's a lot of colors to choose from as well. So there's a wiki page on color values and how to pick them. But I would also say if you want to make good images, or if you have any doubts, you can always email or Slack me as well. But yeah, that's for PyMol. I'm also showing something for VMD. I went ahead and imported a file in VMD because it takes a long time, but I'll show how to use or how to import for VMD as well. When you open VMD, you will find this dialog box and an empty screen here. You go to Files, New Molecule, you browse, and you first load the parameter file, topology file, which is the PalmTop file. Once you load the PalmTop file, you would load your trajectory file, which is your NC file, into the PalmTop file. And once it loads, it will start loading the frames into the topology of the molecule.
This is specific for Amber.
Yeah, this is specifically for Amber, yes. Once all the frames have been loaded, what I like to do is go to graphics, or while the frames are loading as well, go to representation. You would start with just one representation to show the protein well, because when you start, it shows it in, can show this here. It's in element mode and it is in lines, so you can't see anything here. But I generally change it to new cartoon, since this is how we see our protein representations, and change the coloring method to secondary structure. I also changed the material to AO Shiny at the start. I think this is a good material to start off with, but there's a lot of other options as well. You can create a new representation and look, if you want to see specific residues, you can put res ID space, the number of the residue. You can also, if you don't know the number, but you know the name of the residue, you can be like res name and the name of the residue, which will show those residues on the screen as well. For ligands or for any residue, you want to make sure that your drawing method is licorice, because they don't show when you change it to new cartoon. So you change it to new cartoon and the residue vanished. You want to make sure it's in licorice. Another important part is to go to trajectories here and change the smoothing window. And show this, because once the frames are running, if this is at 0, maybe I can show this better on the entire structure. If this is at 0, the structure is really dynamic. So what trajectory smoothing does is, at least for the visual representation, it will take 10 frames. What this number means, it will take 10 frames and make the transition between those frames much smoother. So you don't see a jittery mess on your screen. You will rather see a more smooth transition between frames. I generally keep this at 10 for most of my representation selections.
What did you color by occupancy and element?
So for normal residues or for the ligands, I colored by element because I want to look at the entire ligand. For residue 56 and 58, these are the same residues we were looking at in this. This is 56 and 58. So I wanted to have a way to separate them visually from the ligands. Oops. I wanted to have a way to separate them visually from the ligands, because if they're the same coloring type as the ligands, it's difficult to see where the residues are compared to the ligands. It can be any other method. Occupancy just colors them one way. It can be anything. It can be by mass. By mass is slightly different. These are just preset configurations. There is a way to set your own colors, which is what I've done. The default colors in VMD are really bad. I don't know why they decided to have such bad defaults, but If you want to have your own color representation, you go to graphics, colors. By default, VMD will start with a background color of black, which is 16. So this is how VMD looks by default. I just changed the background to white. If you scroll down the categories, you'll see structure. This way you can color each type of secondary structure on its own color. I prefer blue for the alpha helices and or for any helix, and red 2 for the beta sheets. And the turns and coils are in white, but you can set this to any specific color you want.
One thing, I think you can save this. You can save this visualization scripts as .rc files.
Yep. So the reason it loaded the way I wanted it to is because I saved this as, if you go to extensions, VMD preferences, you can write this settings to a VMD RC file, and you can set this to load your preferred set of settings every time. So you don't have to go through and keep changing the secondary structure colors or keep changing the representations every time. Sometimes it does not save them properly. So one thing I do have to do still, and I have not figured out yet, is it will not set my default render mode to Tachyon RTX. It's just a small thing. I just have to go and change it every time. But okay, so this is colors and representations. For display, again, you have the perspective versus orthographic view. I prefer orthographic, but perspective should be fine as well, depending on what you want to show. I generally like to keep depth queuing off, but either way is fine. Though there are only a few things to change here. Render mode Tachyon RTX would use your GPU rendering instead of normal, which is using your CPU and your RAM. Display settings, if you go, you can turn on ray trace shadows and ambient occlusion just to make it look nicer. One thing to look at here is if you want to visualize or see what's going on around your ligand, but your protein structure is too opaque, what you can do is go to graphics, representations, go to your protein structure and change the material to good cell. This makes it much more transparent, and you can look at the ligands much better in this representation. For this, I was actually looking at one oxygen molecule and how it goes through. If I can see it.
I see the red dot. I mean, it disappeared now, but I saw it before. Oh yeah, there.
Yeah, I was looking at how this oxygen how it enters the ligand. So I think this is I think it enters from the side. Oh, it's still there. Okay. But you can specify specific residues, and for this one, I have specified the same 916 residue ID 916, which we're looking at in PyMol, and I want to look at how this enters and reaches the flavin. So this is a good way, using good cell and coloring the ligands differently, to look at the trajectory visually. It's jittery because I've set this to 10. Okay, this should be much better. For what I did right now, step changes how fast your frames are moving. So step of 10 or 11 it's moving 10 times as fast. So it's good to speed up or down, but once you have the point where you want to visualize, you change it back to 1. And you can visualize and see how the molecules are interacting with each other. There's a lot of extensions in VMD as well for analysis and visualization. There is a movie maker. I have tried and you tried to use it. It has never worked for me so far.
You know how to do it.
Okay. Okay. But you can make good movies in VMD. I've seen people make them.
So you need to have another auxiliary software called as VideoMark.
And you export the images and
import them. Give you so VMD. I don't think it'll give you an MP4 file directly. It's very so what it does is that it basically, when you do this movie generator, it gives you a series of PNG files or JPEG files.
You can actually set it what you want. So I tried with MPG today, but it
No, NPG doesn't work with
Yeah, it
VMD.
didn't
You
work.
need
Yeah.
some other extensions for that.
Yeah.
So the best thing that you can do using VMD is use this and get your frames
Mhm.
as PNG files
Mhm.
and put it into a software called as Video Mark. It is free.
Okay.
And that Video Mark will basically give you use all these frames and give you a video of the trajectory.
Yeah.
That is what I did for my paper.
Okay, that's good to know. I'll try that at some point. I did try the exporting images thing. I didn't use Video Mark. I tried to use another software, but that didn't work for me.
No,
So
I think VMD works best with Video Mark.
Video Mark. Okay.
Yeah.
Okay, that's good to know. But I think that's a very short one on VMD as well. But yeah, that's it. Cool. Both of them.
Yeah, that's great. Do you guys have any questions, Anu and Saswati? And maybe you can turn up the volume too. I don't think they can
Thank
hear
you so
Yeah,
much,
but
Parth, for
I don't
this
think I can.
tutorial. And yeah, I was about to ask about the movie making thing, but it didn't work for me either. But yeah, I think what Siddharth has suggested, I would also try that one.
Yeah, it's Video Mark, right? I'll type it in Video Mark.
Video Mark. I actually have the software open. I can share the link on the
Okay.
channel.
Perfect. And thank you so much for this whole tutorial. It is very helpful.
Oh yeah, no problem. I think I forgot to mention this. There's also other stuff on this GitHub which will eventually also be updated. I think the main one was how to set up a protein ligand MD system. And there's some troubleshooting as well for Amber. You get a lot of weird errors. And I think for my own sanity, I started this at some point because I kept running into the same errors. But I'll keep updating this essentially, this troubleshooting part for sure. And there's some files to go along with it. So this might be useful to anyone who's starting Amber as well.
Oh, do you guys have any questions before we transition?
No, where do you usually find the comments for PyMol, from its manual?
Yeah, I just either go to the PyMol wiki or honestly, I just Google if I want a specific, hey, how do I get the interface residues? That's something I Googled. But I think just starting with the selection algebra is good. If you can get good at this becomes really much faster than using the GUI and doing it manually. But I would just play around with any protein you're looking at and try and change the basic values for that first.
Do you have questions or?
Not really, but I have a question about the PyMol because I'm usually using Chimera X.
Mhm.
They support like making different rotamer for that side chain. Is it like similar function in PyMol?
Rotamers for side chains, right? I think that is something you can do with the mutagenesis tool. Let's return this one. So if you go to wizard and mutagenesis and go to protein, you can set it to no mutation. So it won't mutate to another residue, but you can see what can we show you? Maybe this one. It says pick a residue, right? Did it select one? I think I can show it. Okay, yeah. So you can pick say this arginine, and we can say no change and just change between the different backbone rotamers. Or I think this is an arginine, right? Change from an arginine to an arginine, which is basically no change. And then it should show us the backbone rotamers. I think maybe if I change this to it might be that specific residue only has one rotamer possible. Maybe if there's maybe this one.
I think when you change it to histidine, there were more options, but I don't know. I don't know if it's residue specific.
Okay. It moved up. Oh, yeah. So if you let's go to no change. Yeah. If you go to no mutations and click this, it will show all the different rotamers here. And you can like select which rotamer you want to select. But yeah, that is also there.
Alrighty. Yeah, thanks, Parth. And I'll stop recording.
Yeah.